Now, what we would start henceforth is an area known as so this lecture would be mostly a storytelling session. So, where I would describe things, set up things with a few problems thrown in here and there, and then possibly in the afternoon class we will see some examples of it. Okay. Now, think of the following situation. You have a network router. Think of the traffic going through it. So, what does a network router do? Gets a packet, checks its destination address where it has to go, sends it. Now, this network, this router is a small computing device, right, which has very less amount of space with it, but the data that is going through it is huge, right. Now, say for example, this network company wants to do something with the network traffic that has gone through this router throughout the day. Say for example, it just wants to figure out how many distinct IDs were there. Right. So, each one has a address imprinted on it. So, it just wants to figure out how many distinct addresses to which I have sent the data. Do you appreciate the problem? Now, think of this problem in your RAM model. What is your RAM model? There is a kind of a monolithic memory whose any location can be accessed in order one time. That is a RAM model for you, and each data kind of fits into the width of this. So, 1 unit is the integer that you are going to handle. So, it is kind of the word RAM model. So, your problem is as follows. So, you have an array say having these elements A1, A2, AN, and your question is find the distinct elements or the number of distinct elements. What do you do in your usual RAM model to find out the distinct elements? How do you delete duplicates? How do you find duplicates? So, what time would you take? N square. Okay. So, her algorithm is you look at the first element, run through the array to figure out if there are multiple instances of this, right. So, what you do is you take linear time for each element. So, for the first you take n, for the next you take n minus 1, so on and so forth. If you look at the sum, it is proportional to n square. Can we do better? Hash. Hash is a very precious weapon. Don't use it here and there. There is a saying. I am a Bengali. There is a saying in Bengali which translated to English is roughly like this: shooting cannonballs for mosquitoes. Yeah. So hash is like a very precious weapon. Don't throw it here and there. So I think Venkatesh will have a lecture on hashing tomorrow, and then we will show you uses of hashing. Hash, you can hash obviously, but there are particular situations where you hash, otherwise it becomes too costly. Yeah. So apart from hashing, any other answers? I want to do better than n square. Good. If you sort the element and then just run through. So, if you sort the element, if there are multiple instances of the number, they will be consecutive side by side. Whenever you have a border, you know that one distinct element is gone, right. So, in RAM you can do it in n log n. Can you do even better? Now, see, this area of algorithms is about, algorithms would always talk of efficiency, of doing better, still better, still better. But is there a limit beyond which you cannot get better? That is the notion of lower bounds, which we will also do. So, say for example, if you look at sorting, right. Now, by now you know some n log n algorithms for sorting. If you look at your fast sorting algorithm of bubble sort, by the way, that is my favorite sorting algorithm, bubble sort, you just bubble up n square time, nice algorithm, right. But you are not happy, so you wanted to do even better, you landed up with n log n, your heap sort, merge sort. Quick sort in the worst case is not n log n, but in the average case it is n log n. Then again people brought in randomization. In randomization also you saw that expected case was n log n, quick sort. Next question is, can you do sorting better than n log n? If you can do sorting better than n log n, then this distinct elements is also solvable in better than n log n. So, have you ever heard of a sorting algorithm that outperforms n log n? Have you not heard? Linear time sorting? Not studied? Not studied things like counting sort, bucket sort? Huh? None of you have heard of this? Okay. There are sorting algorithms which sorts in linear time, but there are assumptions on the input, right. So, you have assumptions like the numbers come within a range, then you can have assumptions like they are uniformly distributed in certain range, but without those assumptions on the input, if your numbers are arbitrary, then n log n is a lower bound, one can prove it. The idea for proving such a lower bound is, I will not go into the exact proof, but see, when you talk of lower bounds, so say there is this problem of sorting. Mind you, all these sorting algorithms that you kind of looked at, bubble sort, selection sort, merge sort, quick sort, heap sort, they are all comparison based sorts. That means the machine in which you sort has the power to compare two numbers and tell you that this is greater, this is less. So, this is my machine. So, the moment you want to solve a problem, what becomes very crucial is the machine in which you are solving the problem. Look into this distinct elements problem. It is pretty easy to solve this when you are in the RAM model, right? It is just a no brainer almost. You sort, you are done. But think of the same problem on this network router model. You have probably 1 million, 10 million packets going through this router in a day, and if you want to apply this algorithm, then you have to sort. How do you sort? Because what is the router doing? The packet comes, sees the destination ID, sends it. Until and unless the router has enough space to hold all of these IDs, there is no way that this router can figure out the number of distinct elements. See, the same problem, when I take it from this RAM model to a different model of computation, it becomes extremely difficult, right. So, you appreciate this one, you appreciate this fact that if I change the machine model under which I compute, the difficulty levels of problems change and change dramatically. So, I will give you a machine model very soon, which is actually the streaming, which basically models this kind of network traffic computation. But before I get into that, let us talk a little bit of lower bounds. Now, see this fact that the moment you have started appreciating this fact that, well, this distinct element problem is no longer very amenable in this new machine model of router computation by the router, then you start thinking, well, there might be even impossibility results, right. An algorithm is kind of a possibility result. When you solve this distinct element problem in your RAM model, you showed that it is possible to solve this problem under the RAM model, right. So, it is I have given you a nice algorithm as a proof of the possibility of the fact that this problem can be solved. So, an algorithm is a proof of a possibility. But when I change this model for the same distinct element problem to another model, hey, it seems not possible. So, that means can there be impossibility results? Meaning thereby that we saw that for these distinct elements, if this network router was allowed to store everything, it could have solved it. So, the impossibility result might be something like this, that until and unless you allow me to store everything, I cannot solve this problem, right. So, this impossibility results a kind of this lower bounds. Now, let us come back to this sorting problem. Under this RAM mod, and let us even make this machine model more rudimentary. So, I give the machine the power to compute, rather to compare two numbers, right. So, that is why it is comparison based sort. Now, if you look at your quick sort, your bubble sort, your selection sort, whatever, essentially you compare, right. You compare, and based on the comparison you do something, either you swap or you allow it to remain as it is. So, that is the reason your number of swaps are never exceeds your number of comparisons. So, you measure the number of comparisons asymptotically and you think you are done, fine. Now, coming back to this, so I need to model a machine which kind of has the power to compare. So, the way these lower bounds are proved is as follows. So, you have this comparison based sort. So, you have algorithms for it, say maybe quick sort, heap sort, my favorite bubble sort, merge sort, so on and so forth. These are algorithms to solve a problem. So, now you have a problem, a well posed, well defined problem, and a machine model on which you solve this problem. Now, think of the sorting problem and the relevant machine for it. What it can do is it can compare say two numbers x1, x2. So, in sorting what do you have? You have n numbers and you compare and then do certain things. So, so you sort. So, based on x1 less than x2, rather let me write it this way. To make our life simpler, let us think of these numbers to be distinct. So, I first check whether x1 is greater than x2. If yes, I do something, if no, I do something. Again at a stage I compare two numbers, I keep doing. Okay. So, look at your favorite sorting algorithm and you can model it in this fashion, right. So, for example, bubble sort, you compare x1 with x2, whichever is greater, then you compare x1 with x3. So, somewhere down the line in another of the nodes of the tree, those comparisons will come, and this tree kind of grows. Now, you will have leaves of this tree. So, what are the leaves? When you need nothing to do, that means you have got a sorted output. Now, mind you, a sorted output is any one of the factorial n permutations of the number that you are given. I have made all of the numbers distinct, so you have factorial n permutations, fine. So, my leaves are any one of these factorial n permutations. So, that means my machine model is such that it starts from a location, from the root, makes comparisons and find its way to any one of these permutations, which is a sorted order. Now, what is this? What does this height represent? The number of comparisons that you did. And mind you, for a tree, if you are on a leaf, there is a unique path. There exists a unique path from the root to that leaf, right. So, given your input sequence, there is a unique sequence of comparisons that leads you to your final sorted output. So, now you know the relation between the height of a tree and the number of leaves, right. So, now the point is you can now put a bound on this height to argue about a lower bound on sorting. So, it is simple. If 2 to the power of h is the say minimum height and take log on both sides and you can figure out that h is n log n. So, that is the idea. Now, mind you, in here the lower bound that I was giving you was a lower bound on the number of comparisons that you make, and the complexity that we were analyzing was the time complexity, right. So, we at some point we said that the time complexity is proportional to the number of comparisons that you make, right. So, this n log n is kind of a lower bound on the time complexity of a sorting algorithm, where there is no restriction on the input of the sorting. Mind you, that if there are restricted inputs coming from particular domains, one can even go less than n log n. There are sorting algorithms known as counting sort, bucket sort. There this hashing idea is used in some way. So, but again, as I said, there are enough assumptions and restrictions on the input. So, I have given you an idea of lower bound on the time, but if you now look into this network router problem, the impossibility, so this is kind of an impossibility result, right, that you cannot sort in time less than n log n. So, similarly in the router problem, what was the impossibility that we saw? That until and unless you are storing the entire traffic, nothing significant can be done. So, that impossibility result translates to a lower bound on space. So, we need ideas to prove lower bound on space. So, for streaming algorithms impossibility, we would need ideas to prove lower bound on space. Fine. So, I have given you notions of impossibility results and lower bounds. Let us now enough of storytelling, let us now get a bit more concrete. Let us now define this model. What is this model? That is one characteristic, surely it is large. This is very important. So, I call this to be the string So, I will call each AI to be a token. Okay, what did I write? Now, see, in when I was looking into this RAM model, I could access data in any way I liked. There was no sequence. But here I am imposing a sequence. What does that mean? That you can only see the data in this direction. First you see A1, then A2, then A3, so on and so forth, AN. That is how your router behaves. Fine. Okay. So, the length of the stream is M, and each element in this string takes a value between 1 to n. That is the universe in which each token belongs. Fine. Okay. Now, reading this data in the sequence actually makes your life very difficult. So, once you have seen A2, you cannot see A1 any further. That packet is gone. Okay. So, what you can do? So, there is this notion of pass. P on probabilities. So, there are multi-pass algorithms where, now see, multi-pass means in first pass you read the data as A1, A2, AI, AM. In the second pass also you have to read the data in the same sequence. You cannot alter the sequence. Ideally, we would talk of single pass algorithms. Okay. So, what is just the extra thing that I have? So, you can use some extra space. And obviously, sublinear, because if I allow you linear space, you will store the entire data, right. If the router is allowed linear space, it will store everything and then it can compute anything. So, the holy grail is sublinear space. Ideally, why log n plus log m, or minimum over log n log m? Because see, your universe is of size n. So, to encode each token in binary you need log n bits. You appreciate this? Because to write the number 0 to 7 you need 3 bits, right. This binary representation all of you know, right. So, to count the number of elements in this stream, in a counter I need log m bits, because the stream length can be m. If I need a counter to store how many elements gone past, then I would need a log m bit counter, and to encode each element of the universe I would need log n bits. So, my goal would be to solve these problems in space log n plus log m. But as one would show you that it is not always possible, again then impossibility results would come, and then people get up to say square root n, but again you know the main goal is to remain sublinear strictly. So, that means it is small o of n. Okay. So, Venkatesh has already done this Mishra-Grice algorithm for you, right, estimating the frequency. Let us look at, I think this he has not done, let us look at a problem like this. You understand this problem? So, my input stream is say for example, you know, if I am looking at the numbers this, so my input stream could be 5, 3, 1, 2. Right? So, one element missing, you have to find that. What n into n plus 1 by 2? You have a write a equation from 1 to n. See, in RAM model again it is very easy, right? What do you do?
Calculate the sum and subtract it from sum of n plus 1.
Okay, that is a nice idea, but how do I do it in streaming? Okay, I take forward his idea. What I do is, so I have been told that my stream is say sum a1 a2 distinct an minus 1 and sigma is comes from a permutation of n. So, the first element comes, what do I do? What do I do now? Yeah, go ahead. You had a nice idea. Go ahead.
Declare one sum variable and add every
Add every element. Okay. So, his idea is as follows: declare a sum variable. So, that means it is a space. Huh? So, you add this. In the next step, make sum equals to sum plus A2, go on. Fine. So, the sum is growing in size, right? A1 plus A2 plus, what would be the size that you need for the space that stores this value sum? Linear space. Why? Can I put a bound on this value of sum? Sum of these elements, right? It cannot get more than, right? Which is big O of n square, right? To represent a number n, how many bits do I need? Log n. To represent a number n square, how many bits do I need? Right? Order log n. So, to represent any number that is poly in n, I require order log n, right? You agree to this? So, what I do? My extra space is log n and I am happy with that. So, I store the sum, at the end I subtract it from n into n plus 1 by 2, then I have found the missing element. Okay. Now, I change the problem a little bit. How would I change? Instead of 1, make it 2. What do you do? Does your idea still work? What do I do?
declare one binary array with true or false.
Declare a binary array with true or false. Binary array of what size?
Take an array with
Huh?
you will take another array, sir.
Another array. I have not taken an array, it was just a log n bit counter. So, the idea is not very far from what you did earlier. See, I have two variables that I need to fix. So, that means I need two equations to solve them. One comes from here. The other comes, what I do is, Right, I square and keep the sum. And I know the sum of 1 square plus 2 square plus up to n square. Subtract it. Still you can do it in log n time. Right? Did you get the idea? Yeah. Okay. Now, you understand that things would start getting difficult. Now, let us formalize a few things. One is we would start talking in terms of the quality of the solution. Professor, this class goes up to 12:45. So, quality of the solution. So, what I have is a stream phi. Now, see this distinct elements problem that I gave you in the streaming model, I cannot exactly solve it, right, but there may be an approximate solution, right. So, what I do is first I define so say for example, in this problem of finding missing element, what were you throwing out? The sum, right. So, for distinct elements you have a number, that this is the number of distinct elements. We will see many other problems, but for any problem I can abstract it out as that given the stream I will give you a number as an answer. Fine. Number of distinct elements, approximate counting again a number, frequency moments we will see again a number. So, I see that the output that this algorithm, streaming algorithm would give is a real valued function phi, fine. So, phi takes sigma gives you a real value. A is say your streaming algorithm. So, as I have seen that the streaming algorithm throws out this value. Now, for many of the cases this streaming algorithm would not be able to solve the problem exactly, it will only solve it approximately. So, we will look into this distinct elements problem and give you an approximate solution. Now, what is a good approximate solution? You should be, your output A sigma should be as close as possible to this phi sigma, right. So, we would now define a notion called an epsilon delta algorithm. Where epsilon is an error parameter and delta is a probability measure. Most of the cases, this Mishra-Grice algorithm that you saw was a deterministic streaming algorithm, this finding missing elements was another deterministic algorithm, but most of the streaming algorithms would be a probabilistic algorithm, would be a randomized algorithm. Because without randomization you would see that almost you would be able to do nothing. So, make a comment that for most of the cases this would be a randomized streaming algorithm. So, this is the error. So, this is what my algorithm gives, this is what the exact value was, by the exact value this is greater than an error parameter. So, you can think of this as A sigma minus phi sigma greater than equals to epsilon into phi sigma. What is this delta now? These are randomized algorithms, right. So, I would say the probability of this is bounded by delta. Or I should not say multiplicative error. So, this is known as a multiplicative epsilon delta algorithm. Now, there are situations where this is very close to 0, then this definition is too strong a definition, right, because this thing will now go up too much. So, for that there is another definition which is known as the additive approximation. So far so good? Okay. Now let us look at a problem like this, which kind of models this network thing. This was a classic paper by Paul Witter around mid 90s, mid 80s, 1980s of the previous century. So, this aptly captures this network router problem. Okay. So, the problem is as follows. So, this router has this traffic going along. So, it has to store a sample of size which is very small compared to the full traffic that has gone by, but the sample should be a uniformly random sample. Now, to draw a uniform random sample out of a sequence of traffic whose final value you do not know, because this router only at the end of the day will know how much traffic has gone past, right. It has a fixed size on its router board, so say of size k, that it knows, but it does not know the length of the stream. Someday it could be 1000, someday it could be 1 million, someday it could be 100 million, but the sample that it has to store has to be a uniformly random sample from that stream. Now, you must be appreciating this fact that if it is a probability, there should be something above, something below. Now, this below thing, it does not know till the stream has gone past. How can it draw a sample that is uniformly random? You understand the problem and the difficulty of it? Okay. So, my problem is sample k is much greater than k. So, k is the size of the reservoir, you might say. So, this is like m, and you have to store some part of it, but that part has to be uniformly random. So, this has to come down to a reservoir of size k, much smaller than m. What do you do? Swap with. See, the first part is easy. For the first k elements in the stream, just copy it, right? So, think of an I which kind of loops over this. So, I equals to 1 to k, our life is pretty smooth. See an element, put it into the reservoir. I plus 1th element comes. What do I do? Either I have to let it go, but if I allow it to let it go, then never can it be in my sample. So, I have to take a few decisions, right? You have to take that decision, because that decision has to be taken now only. Once it has gone past, I cannot take a decision on this. So, this is one decision. Do I need to take other decisions? Right, very good. The second decision, if yes, so let me name this reservoir as R. Now, as you have seen for your say quick sort, If you always say that my first element is the pivot, then your life is in problem, right? So that is why what did you do? You picked the pivot uniformly at random. So the best thing in here, if I have taken a decision to replace, what I would do is I would pick a random number between 1 and k and then replace that value. So that will allow me some randomness, so that I can use probability and do some calculations over it. Right, this is like is okay. Replace a random entry of R. Now what about 1? 2 is easy. What about 1? That also has to be a probabilistic decision, right? I cannot deterministically take a decision whether this has to go in or out. So, with a certain probability, I will decide that this element will get into the reservoir. This is not going to be a deterministic decision henceforth. It will be a probabilistic decision. So, what would I say? That with certain probability, replace this element, or rather put this element into a random entry of the reservoir R. Now, is this making some sense with you? Because till now you were accustomed to yes, no deterministic answers. Now, these are probabilistic answers. I will say yes with a certain probability. Fine. Think of this. The sample that you are going to take of size k has to be uniformly at random, right? Okay. Now, for this element and say for example an element towards the end, which one you think would be more probable to get into the reservoir? Given a choice, which one would you want to put into the reservoir? Elements towards the beginning or elements towards the end? End. Why? See, at the end, whether you put this or this, is it hardly going to make any difference? Mind you, this reservoir has to be an uniformly random sample. So, that means towards this end, whatever is in the denominator, so 1 by n and 1 by n plus 1 with n large looks almost the same, right? So, our hunch tells us that the probability should kind of go down as I go towards the end of the stream. Because really I do not know where the stream is going to end, I do not know m. So, what I would do is I would try to kind of make the probability proportional to the reservoir size by the length of the stream seen so far. So that an element in here comes with a probability of k by I and an element there comes with a probability of k by m. Mind you, there is obviously always a chance of this element to get into the reservoir, and I am not ruling out that chance, but I am making it get into the reservoir with a cost, because if your stream length is very big compared to k, the probability of this element to get into the reservoir is small. So, it perfectly makes sense to make this probability as k by I, where I is the length of the stream seen so far. We will see if our hunch translates into a correct mathematics. That obviously we need to prove. But this intuition kind of may be working. At least this probability should be variable, that much you understand, right? So, the variability I bring in through the stream length, the numerator keeps fixed at k. Okay. So, my algorithm is as follows, pretty simple algorithm, we will then analyze it. So, what I would do is, so is the algorithm clear? Professor, I might overshoot by 5 minutes, I think, yeah. So, is the algorithm clear? Think of writing a program for this. If you have to write a program for this Uddalok and Devor should tell you later, how do you do this is very important, right? Think of this, when you write a program, earlier it was just choosing xi to be in the reservoir or not. Now you are being asked to make this decision with a probability. So, think of a subroutine that given this element xi and the probability k by I takes a decision whether, see, finally what is happening is deterministic, either this element is going into the reservoir or not, but the decision in itself is probabilistic. Think this over. How do you write a program to implement this? Fine? Okay. So, say for example, now you have a black box which kind of with the probability k by I can decide whether this element xi is going to replace or not. So, this black box has fixed that probability and given you the decision whether xi is going to replace, get into the new reservoir or not. Once that decision is taken that you are going to replace, which was a probabilistic decision, then you have to fix which random entry of the reservoir to replace. You again need a subroutine for that. So, that is done, right? Okay. Now, how do I prove this result? Because see, I do not know the end, but somewhere down the line you will say that all packets have gone. So, the best bet of proving this is I will maintain an invariant that at every step whatever is there in the reservoir is an uniformly random sample. So, if I can force this invariance at every step of the algorithm, then it should hold at the end as well, right. So, I will for any integer set t, I will show to you that it is that the reservoir is an uniformly random sample with that probability of k by t to be in the reservoir. Fine. Okay. So, this kind of proofs are known as invariance proofs. What? So, I prove a thing for all steps, for a step and then t runs towards the end. Okay. So, what am I required to prove? Okay. So, R was the reservoir, I use the subscript T to denote the status of the reservoir after T elements of the stream has been seen. So, I want to prove the following claim and then I would be done. For all t greater than I, probability xi belonging to RT is equals to k by t. Here I is the index of the stream. So, the proof is an induction on T. How I view time? So, T and I is the index that maintains the condition of the loop. So, I runs from somewhere to up to T. So, at your ith thing the element is xi. Now, see, mind you, the algorithm starts by first figuring out the first k elements into the reservoir and then it works, right. So, I will do it for the entire thing. So, I runs from the beginning to T. So, that means if I look at k, the reservoir size, so k can be either in this region or in this region, right. If k is in this region, that means I has grown over the reservoir size, and if it is in this region, it still filling up the reservoir. So, in this region I is greater than k, in this region I is less than k. So, k is in okay. Now, I look into the base case. Mind you, the induction is on T. So, case 1 is if I is less than k. I is less than k. So, I am in this zone. Okay. So, convince yourself that in this zone the base case will be when t is equals to k. Right. So, I am in this zone, sorry, I am in this zone. So, the base case would be when k is equals to t, or rather t is equals to k. And you can verify that the probability of xi belonging to R k should be equals to 1, and that is equals to k by t. For the other case, I am going a bit fast over this, you go back and check yourself. If you have doubts, ask later in the tutorial, or I would be around. So, in this base case will be when t equals to I, when t is equals to I, right. which is also k by t. Now, let us get into the induction step. This is what we are interested in. So, what about an I that is less than equals to t, mind you. So, do not bother about the base cases too much, these are boundary cases. If you go back and read a little quietly, they should be okay. But once the base condition holds, now I have a situation where I is the loop index that is going up to t and my induction is over t. So, I would rather look at t. So, I will assume my induction hypothesis up to t and I would prove for t plus 1. So, I now look at any element x I, mind you my I is less than t, and I have to figure out what is the probability with which x I is going into the reservoir at time t plus 1, but the induction hypothesis is true till R t. R t is the status of the reservoir after the tth element has gone, right. So, that is what I have written. Is this uniformly random condition still holding? That is my question. Now, see, for x I to belong to R t plus 1. So, what is R t plus 1? The reservoir indexed with the time. For x I to belong to R t plus 1, what must have happened? X I was there in the reservoir. So, that means x I belongs to R t and the new element, the t plus 1th element must not have replaced it. So, I now get into the realms of conditional probability. Okay. This statement is okay with you? That for x I to belong there, it must have been there earlier and not replaced. Fine. Now, I use the chain rule. On the first part, on this part, induction hypothesis would apply, right. My induction is on t, remember. So, on this part induction would hold. Into probability x I is not replaced at time t plus 1 given that xi belongs to Rt. Agreed? This is just the chain rule. Now, my induction hypothesis tells me that this is k by t into conditional probability is a probability that we have proved. So, I can now take complements. So, this is 1 minus probability of this is because of induction hypothesis. Agreed? Replaces and the probability of replacement. So, this should be 1 by k into k by t plus 1, right. I am going to remember the entry that I am going to replace is a random entry. So, that has to be uniform 1 by k, and I replace with what probability? K by I, here I is t plus 1. Now, just see what is this. So, this is for a random entry in R, and this is the probability of replacement. If you work this out, this should come to, that is what, and that is what we set out to prove. So, now you can have a job for a good network company, if you can write that program. It is a nice implementable algorithm with a theoretical guarantee. With your, I am from the days of C, so you are all Python people. In Python, this should be a code this much, 4-5 lines maybe just. Ki Devarshi, 5 lines Python, something like that, yeah, 5 to 10 lines at most. It is that simple, right? But the problem was looking insurmountable at the beginning. I did not know, see, the challenge of the problem was I did not know the length of the string. So, this uniformly at random was not making sense to me. How did that magic happen? The magic actually happened with the choice of this probability. Now, how do theorists actually do this? So, see, when you read the paper or when you read the book is written from the beginning to the end, but mathematicians usually mostly do the other way around. They look at this calculation, right? They get their hands dirty on this calculation, and from there they fix out the probability. If you look at this calculation at the beginning, see, just given this problem and the sense of the algorithm, it would not be difficult for you to write that first line, right? It is just not difficult to write the first line. Once you write the first line, writing the second line is also not difficult. It is just the chain rule. Once you write that, 1 minus writing that is not difficult. Now, this part of the calculation actually fixes that probability k by I. So, you now know that for this to turn out to k by t plus 1, I should get things like this, and that kind of gives you a back calculation idea that, well, if I fix the probability as k by I, then this calculation would go in very smoothly. See, it is uniformly at random, right. So, you know that the numerator should be k. Fixing the denominator was the challenge. The calculation gives you that idea, what should be the denominator. So, what remains is to write a program that does fix that probability, choosing and deciding with a probability of k by I, and this number is going to change, you understand. At the very beginning it is k by, say if your reservoir is k by 10 of size 10, then you are looking at k by 11, k by 12, so on and so forth. So, these probabilities are changing at each step. So, this is kind of your first non-trivial randomized streaming algorithm.